Right, we're back for the second part. You guys might have wondered, like I did when I was a kid, how did they actually get to find out what absolute zero is if like it's only theoretically possible and it never exists in real life? And here's how they did that. So if we think of a graph, and I'm only going to show the first and the second quadrant, okay? So this is like your normal graph that you normally see. And if we have temperature in degrees Celsius here, and then if we have our volume here on the y-axis, right? This is volume. Now, what they did is if they measured, let's say we measured 100 degrees Celsius, all the way down to 0 degrees Celsius, right? So you would get this trend, and you would get this trend right here, right? And we would get to like a volume that's maybe about there. What you can actually do is you can extrapolate this all the way back, right? And get to a point where it matches. Now, this is not the scale. This is just a sketch, but this temperature right here, this x value would be negative 273, and now the exact number is 273.15. Okay, so that's how they were actually able to find absolute zero. That point is that magical point at the point where you would have no volume and so therefore you would just have no kinetic energy. It only exists on paper though. All right, so we're going to move on into Lusac's law. And now this one is very similar to Charles' law, except now we have pressure on top instead of volume. Okay. Now you must again use the Kelvin temperature in the denominator. The reason, if you use Celsius, we can have a 0 degrees Celsius, and you are not allowed to divide by 0, right? You can have negative temperatures, and that's just going to mess it all up. So we don't have negative temperatures in Kelvin, so that works. So that's why we use the Kelvin temperature. All right, so example 16, the gas in an aerosol can is at a pressure of 1 atmosphere and 27 degrees Celsius. It's been a long day. If I take 27 and if I add 273, that's magically exactly 300 Kelvin. All right, it's almost like I planned it. If the can is thrown into a fire, what is the internal pressure of the can in atmospheres when the temperature reaches 927 degrees Celsius? So 927 plus 273 is equal to 1200. Okay, good. So I bet we could do this without a calculator. The pressure is 1 atmosphere and 300 Kelvin. So we have 1 atmosphere and 300 Kelvin. What is the pressure when it gets to 1200 Kelvin? Are you guys seeing a proportional relationship from here to here? How much did I increase the temperature? Yep, I took the temperature and I multiplied it by 4, right? You see that? So that means I'm going to take the pressure and I'm going to multiply it by 4. You see that? This is called a direct relationship. Everybody see that? So for x, that means that you would get to 4 atmospheres. Easy peasy. Got it? Exactly 4 atmospheres. Piece of cake. We don't even need a calculator. I'm pretty sure the can would fail before would explode before 4 atmospheres, but hey, go ahead. Do not try that at home. Why does an increase in temperature lead to an increase in pressure? for a fixed volume. So if we have a fixed volume, we have two boxes that are the same volume. Why does an increase in temperature lead to an increase in pressure? Well, if we have three circles again, we have short arrows here, right, for our low temperature. And then we have longer arrows for our high temperature. Boink, boink, right? You can easily tell that we definitely get more collisions here. All right, so therefore, more collisions, therefore a higher pressure. Everybody good? That's exactly how that works. So that one's much easier to see. Be ready for something like that, and be ready to explain it using a particle diagram. If you ever get one of these questions, kind of like that, feel free to draw a particle diagram. You know, sometimes a picture is worth 1,000 words. You don't have to completely write out your thoughts in a full sentence. If you draw diagrams, like I did, annotate them, and then show that you know what you're talking about, that can probably count, all right? Just make sure you annotate them. Don't just draw pictures. All right, so for the combined gas law, last little page right here, we got the Boyle's law, the Charles law, and the Lussac law can all be combined into one single expression. So you actually don't even need those other three that I taught you. You can just use this one the entire time. If one of them is being held constant, you just ignore it. All right. So a container with an initial volume of 1 liter is occupied by a gas at a pressure of 1.5 atmospheres and 25 degrees Celsius. So I'm going to say that that is 298 Kelvin. 298 Kelvin. By changing the volume, the pressure of the gas increases to 6 atmospheres as the temperature is raised to 100 degrees Celsius, and that is 373 Kelvin. All right, what is the new volume? So, it says example 17, doesn't it? It shouldn't. We'll just call it example 17. Go with it. We got P1, V1 equal over T1 equals P2, V2 over T2. Okay. So the initial volume is going to be 1.0 liters. I'll keep the units just so that it kind of makes sense when we look at them later. And is occupied by a gas at a pressure of 1.5 atmospheres. So the pressure is 1.5 atmospheres. And the temperature is 298 Kelvin. Great. And the pressure is then increased to 6 atmospheres. We want to know the new volume because the temperature is increased to 373 Kelvin. So we've already done those Kelvin switches and we've already done everything. So there we go. This is the easiest way to solve it. We want to isolate X. So we're going to get everything that's attached to X on the same side. And we're just going to multiply it by its inverse. So we're going to multiply by 373 over here. 373 is going to be on top because 373 is on bottom here. That way they cancel out. And I'm going to put 6.0 over here. That way they cancel out. Now the units will cancel out as well over here. So those all go away. So I'm going to put 373 over 6.0. It's oddly satisfying to cancel units. So now I just have 373 times 1.5 times 1 divided by 6 divided by 298 equals 0.315. How many sig figs? Just 2. So 0.31. Great. 0.31 liters. That is my answer. I'm done. I put my box around it. I'm good to go. Here you go, teacher. All right. So example number 18, a 700 milliliter gas sample at STP is compressed to a volume of 700 milliliters, 200 milliliters, and the temperature is increased to 30 degrees Celsius. So cross that out. What is 30 plus 273? That's 303. What is the new pressure of the gas in atmospheres? So I want to know my new pressure in atmospheres. Great. So what is STP? STP is standard temperature and pressure. Okay. So what is standard temperature? That is 0 degrees Celsius. And what is standard pressure? That is 1 atmosphere. That's easy. So if it says it's at STP, it's giving you 2 numbers and 3 different. It's giving you 3 letters, but it means 2 numbers. You could also say it's 273 Kelvin instead of 0 degrees Celsius. Okay, so I've already had my temperature. I already had my initial volume. So example number 18, I have my initial pressure is 1 atmosphere because we were at STP. My initial volume is 700 milliliters. And my initial pressure was, my initial temperature was standard temperature, which is 273. All right. Now, what is the new pressure if the volume is changed to 200 milliliters and we have 303 Kelvin? Cancel out those units. 1, 2, 3, 4, gone. So we're left with atmospheres. That's good. Now we're going to cancel out the numbers that are attached to my variable. So I got to cancel out 303, so I got to multiply by 303 on top, and I've got to put 200 on bottom, and then I've got to multiply by 303 on top and put 200 on the bottom. Good. So 303 times 700, I skipped the 1, divided by 200 divided by 273 gives me 3.88. And should I use 3 sig figs? Yes, I should. So I use 3 sig figs. So I'll take the first 3 digits, 1, 2, 3. My 4th digit is my rounding digit, so 4 will round down. So I'm just going to call it 3.88. And atmospheres. I am done. Have a great day.